One application of what we've been doing, which is this integration and specifically definite integrals, is we can find the average value of a function. So typically when you're trying to find like an average, like let's say you took 3 tests this year and you want to know what the average is amongst them, usually what you do is you just like add them up and then divide by how many there are, right? That's usually what we mean when we say average. Although if you're in a statistics class, if you're in AP Stats, you'll know that there's multiple different averages, right? There's mean, median, mode. Those are all different averages. When we usually say average, we're talking about mean, typically. Not always, but in calculus we will be. So when we talk about the average value of a function, this can, pose a little bit of a tricky problem for us, because if we want to know, like, what's the average value on this curve down here, and let's say between 0 and 6, there's not like a finite number of values we can just add up and then divide by however many there are, right? So we have to approach this a little differently. Okay, so let's say that this function represents the rate at which a Starbucks worker gets tipped over a 6-hour shift. So this is not indicating how much they're getting tipped. It's the rate at which they're getting tipped, like how many dollars per hour. Okay. So, part A says, what is the greatest rate of tipping when her shift, and when in her shift was she earning at this rate? So just by looking at the graph, where does the greatest rate of tipping occur if this function is describing the rate?
At the third hour of her shift.
Yeah, at the what? What'd you say?
The 3.
Yeah, t equals 3, right? You can see what's happening there is we have a local maximum, right? Or a relative maximum. And so right here is where we're going to have the greatest rate of tipping. Now, this one is pretty clear from the graph. You can also tell that this is definitely going to have to be at t equals 3, because this is a quadratic, and the graphs of quadratics, parabolas, are always symmetrical. And so if we have x-intercepts at 0 and 6, that maximum has to occur at 3. So we know it's happening at t equals 3, but what is the greatest rate of tipping? What is the y value of that local max? It looks like it's probably 18, but do we know that for sure?
Yes.
Okay, you can plug it in. Okay, so we know it's at t equals 3. Now, let's say that it wasn't so, for lack of a better word, obvious. Like, let's just say maybe it was like offset a little bit. How could we find that local maximum using calculus? How do we find the location of a relative maximum point if we can't use some of these other simple methods to find it? Yeah.
Derivative.
Yeah, use the derivative of it. And what has to be true about the derivative at that point? It's got to be equal to 0. All right, so even though with this problem, we can tell that it's going to be $18 per hour. Well, let's go ahead and just write our answer here. So the greatest rate of tipping was $18 per hour. And that happened at t equals 3 hours. Now we can see that point pretty clearly on the graph here. Now, I'll go pretty quickly through this, but just for the sake of argument and kind of reminding you how you would find this otherwise, you'd find the derivative. You'd find r prime. And you'd set that equal to 0, because we're interested in where this slope is 0. Yeah, so we'd set that negative. First we'd have to find the derivative. What would that be? Negative 4t plus 12. All right, subtract 12 from both sides. We get negative 4t equals negative 12. Divide both sides by negative 4, we get t equals 3. So it's nice when the graph kind of jives with the algebra there. So yeah, it is at t equals 3. And then, like I said before, you could just substitute that back into the original equation to figure out what the y value is. Right? So negative 2 times 3 squared plus 12 times 3 is going to be 18. Now, if this were something a little bit more complicated, let's say we had some polynomial that wasn't quadratic and it had a bunch of relative max and mins, you'd also have to go through and make sure that the point that you found is the point that you're interested in, verifying, for instance, that it's a maximum instead of a minimum, and that sort of thing. We're not going to go through all that, but I think it's worth bringing back up, at least for a minute here. Okay, so let's move on here. Our overall goal here is to figure out how we can find the average value of this function. In other words, on average, how much did she earn per hour? Okay, so we can see the maximum rate was at $16 per hour. What was the minimum rate?
0.
0, right? Like at the very beginning and the very end of her shift, her rate is 0. Okay. And in between there, it fluctuates, right? Goes up to 18, comes back down to 0. But if you had to guess, just by looking at the graph, let's throw out like some numbers here, maybe think about like where you're coming up with these numbers. What would be like a decent estimate, just from looking at it, what you think the average rate might be?
9, because it's
9?
consistent.
Okay, so 9, we say 9. Now, so I assume you said 9 because that's half 18, right? That's like halfway up, halfway down.
And then it's just perfectly parallel. So,
Perfectly parallel, okay.
on both sides. So
Yeah.
You know that it's not just going to go up. It's not an path with extra curves. It's just extra.
Now, let me throw this out there. We're looking for like an average, right? So, like if we're trying to find our average grade on a test, we would just add them all up equally and then divide by how many there are. So my question is, if our answer is 9, is there like the same amount of time that she's making more than $9 per hour versus less than $9 per hour? Like if I divvy this graph up, say, okay, well, here's where she's making 9, here and here. So I'll say roughly here and here. Is there more time in green here? You can't really see that very well. Or purple? Purple. Like I think it is maybe a little close, but I think probably purple, right? Like there's a little bit more time going on. This is like we'll just approximate 0 to 1, and then maybe like 5 to 6. So that's like a total of 2 hours, right? And that leaves us with like roughly 4 hours in between. So is there an equal amount of time that she's making less than $9 versus more than $9 per hour, I should say? No, there's a little bit more time where she's making more than $9 per hour, right? So what does that tell you then about what the average should be? Should it be more than 9 or less than 9? Probably more. And what we're looking for is that number that sort of like splits it in half, right? Okay, so we're going to say, yeah, there's not really a right or wrong answer for B because we're just throwing some numbers out there and thinking about, what would be a good estimate. Another way you could potentially make an estimate here is just by like sort of doing the classic average formula and just picking as many points as you can find on here and saying, okay, well, at t equals 1, how much is she making? At t equals 2, what's the rate? At t equals 3, get these data points, add them up, and then divide by how many data points you chose. Now, it's still going to be an estimate because to really get the exact value, we need infinitely many of those. But at least, kind of like with a Riemann sum, if we pick some of the numbers, we can start to get a decent idea. What do you think?
Yeah. 35 thirds.
35 thirds. Okay, so what would that be? 35 thirds. Let's see, 35 thirds. Okay, so how'd you come up with 35 thirds? I'm curious.
I did a derivative.
You did derivative. Okay, so talk to me. Be more specific. Where that? So the derivative of r. So you did r prime, which was the negative 4t plus 12. Is that what you're saying?
Use the wrong word, not derivative.
Oh, okay. All right. Oh, Riemann sum. Okay, so you were looking for like the area under the curve,
Yes.
right? And you came and so which Riemann sum did you use out of curiosity?
Trapezoidal.
Trapezoidal. And how many intervals did you use?
6.
6. Okay, so like you did like this, found that. So this is kind of what you're thinking, right?
Yeah.
Now, what does that area give you, like in this context?
70.
Okay, so 70. But what does that 70 represent?
$70 in tips.
So 70 total dollars in tips, right? So remember that when you find that integral of a rate of change function, it gives you the net change in whatever that unit is. So in this case, dollars, right? So if you were able to find that area, you could give me the number of dollars she made, right? And so you said, what did you get there? 72 or 70? So you got 70. Say, okay, well, if she made $70 in that 6 hours, well, I assume you did 70 divided by 6, right? Divided by 6 hours, right?
Yeah.
And you got your fraction. 5 over 30, or 35 over 3. Yeah. And so that works out to be what, like $11, 11 and 2/3, so $11.66.
Yeah.
Okay, so our first estimate was $9. Okay, and that was just like, sort of our first guess there. Second guess is $11.66. And I think we're getting a little closer to what the actual value is, because after kind of hearing what his strategy was there, there's a little bit of an error in that, right? Where does that error come from? The Riemann sum inherently has an error, right? We're not finding the total area, we're just estimating it, right? Okay, so how do we find the total area? If I want to find the area from 0 to 6 of this function, negative 2t squared plus 12t, that area will give me the net change of the amount of money she had, or in other words, the total amount. The total amount of money she had, or earned, I should say. We want to find the antiderivatives, which would be, what would that be? Negative 2/3 t cubed plus 6t squared, right, from 0 to 6. So we need to substitute 6 and 0 in there. So first I'll substitute in 6. Negative 2/3 times 6 cubed plus 6 times 6 squared. Ugh. And then minus, and a plus c. Throw that in there. Minus, well, you just plug in 0 for t. You're just going to get a bunch of zeros, right? So now we can evaluate this. Negative 2, well, okay, 6 cubed. 6 times 6, you might need to help me out here. 36, 216. Okay, so 216 divided by 3, might have to do a little scratch work over here. 216 divided by 3 is going to be 72. And then 72 times 2, 144, I think. So negative 144. Nope. Okay. Well, what should it be?
Oh, no, sorry.
Yeah.
Don't ask me questions.
Okay. So, and then 6 squared is 30. Okay, and then we have the 216 again. So plus 216. Okay, so negative 144 plus 216. Arithmetic's getting a little tricky here. Let's see. So that'd be 0, carry the 1, 5, 6. Oh, wait. That's negative. My bad. That's not even positive. Okay. Still waking up this Monday morning. 216 minus 144.
72.
Is it 72? Okay, thank you. Oh, it's tough.
Then you divide that by.
Okay, well, so that's it. Hold on, that's it, right? That is the total amount of money that they made in the 6-hour shift. Now, the estimate with that trapezoidal sum you came up with, was it 70? Is that what you got, Ethan? Yeah, 70. So this is pretty close, right? Okay, so if we want the average rate of dollars per hour from tips, we need to take that total amount and divide by the total time. Right, so $72 divided by 6 hours gives us $12 per hour. So to calculate the average value of this function, you've got to integrate it on whatever interval you're trying to find the average over, and then divide it by how long that interval is. So it's still the same kind of idea of like adding up all the tests and then dividing by how many tests you have. But this is how it would work if you had infinitely many tests. Yeah. Sometimes it feels like that, I'm sure. Okay, so let's just give ourselves a little formula here, kind of break this down. Okay, so if we want to find the average value of the function, and by the average value of the function, I'm talking about the y values. Okay, the average y value. Or like the average height of the function. Sometimes you'll see it written like this, like f average. So it's the average value of the function is equal to the total area under the curve, which we can find using the fundamental theorem of calculus, divided by the length of the interval. All right, and that's what this little thing down here is, right? This is the length of the interval, or like the base length. And then the stuff up top, this part, is the area under the curve. Sometimes you'll see this formula written like this. 1 over b minus a times that definite integral. It's the same thing, basically. I've seen it written both ways. I don't know if there's really like an advantage one way or the other. But that's it. That's how you find the average value of a function. Okay, so this is just one little application of this fundamental theorem of calculus. That's all we're going to do today. It's a short lesson today. Next time, we're going to get into part 1 of the fundamental theorem of calculus and really kind of dive pretty deep into that one. Does anyone have any questions?